Okay, so I'm going to continue from where I left off. I've got a few more things to do in section 7.1. And then we start 7.2. I'm definitely not going to make it as far as I expected to, but that's okay. I definitely wanted to do a bunch of different examples from 7.1 to make sure that you can see what's going on with integration by parts problems. So the last couple examples I have from 7.1.2 are integrals that require both substitution as well as integration by parts. So these are ones in which one step is going to be substitution, another step is going to be integration by parts. One thing I'm going to mention here, usually when we're doing substitution in these sort of contexts, it's oftentimes useful to use a letter that's not U, because integration by parts already uses the letter U, and so there's oftentimes a conflict here. And sometimes you do the substitution before you do the integration by parts, sometimes you do substitution after you do the integration by parts. It depends upon the question. So the first one I'm going to do, example 7, is finding the integral of sine inverse of x dx. So here we have integral sine inverse of x dx. So here, remember, one of the guidelines is if you have a ln or a sine or inverse trigonometric function, always call that thing u and the rest dv. So this sine inverse of x is going to have to be my u. dv here is just going to be dx, or 1 dx if you want to think about it that way. So u is sine inverse of x. dv is 1 dx. So du is the derivative of sine inverse of x. That's 1 over the square root of 1 minus x squared. V is the antiderivative of 1, which is just x. So what this will give you is uv, which is sine inverse of x times x, minus the integral of v du, which is x times 1 over square root of 1 minus x squared. So that's, so that's the first step of this integral. Now this thing here is something you can't integrate right on its own already, right? This is not an easy integral to do. It turns out that, though, that integration by parts is not the way to finish off this integral, that substitution is the way to finish off the integral. And the reason you can see that is because here you've got a square root of something complicated. You have an outside function and an inside function. Any of those sorts of situations, you're always going to want to try to use substitution to finish it off. Now here, the variable I'm going to use for substitution is going to be t rather than u, just because I used u already above. So t is 1 minus x squared. dt is negative 2x dx. Now here we just have x dx rather than negative 2x dx. So x dx is dt over negative 2. And so what we're going to get that first guy is going to give you x times sine inverse of x. The second guy is going to give you 1 over square root of u times, d square root of t times dt over negative 2. We bring the negative 2 out front. I have x sine inverse of x, or plus 1/2. Integral 1 over square root of t is the same thing as t to the negative 1/2. And the antiderivative of t to the 1/2 is t to the 1/2. T to the negative 1/2 is t to the 1/2 over 1/2. So here we have x sine inverse x plus that guy. These 1/2s will cancel. So we'll get x sine inverse of x plus t is 1 minus x squared to the 1/2 plus c. This is the antiderivative of sine inverse of x. So again, first we had to do integration by parts. Integration by parts gave you this integral. And then we did a substitution. T equals 1 minus x squared. And that substitution allowed you to evaluate the integral that we had left. And that's what we got as a final answer. Any questions about example 7? Okay, example 8. Then. So here in example 8, we have the integral from 0 to pi, e to the cos t sine 2t dt. Now the first thing to mention is that to even do this integral, we need to have the actual formula for sine of 2t. Sine of 2t is 2 sine t cos t. I'm not going to make you folks memorize those formulas for this course. Those are going to be on the formula sheet. So the fact that sine 2t is 2 sine t cos t, that's going to be on your formula sheet. So this I can write like this. 2e to the cos t sine t cos t dt. Now we could try to do this by integration by parts, but we'll have great difficulty, and the reason is because here we have a composition of two functions. So to get rid of that composition of two functions, I'm going to want to do a substitution. Oh no, I'm not going to use u. I'm going to use x. X equals cos t. So dx is, the derivative of cos t is negative sine t dt. Now we don't have a negative sine t dt, we just have a sine t dt. So dx, so negative dx is sine t dt. We also need to change those limits of integration. When x is 0, cos t is cosine 0. Sorry, when t is 0, x is 1. Because the cosine of 0 is 1. When t is pi, when we're at the upper limit of integration, sorry, I'm blocking the board from that half of the class again. When t is pi, x is the cosine of pi, which is negative 1. So the integral we're going to get is integral from negative 1 to 1. The 2 is going to be here. The cos t there will become an x. Sine t dt will become a negative dx. And this cos t will become another x. So we'll have something that looks like that. Integral from negative 1 to 1, 2 e to the x times x, negative dx. And the 2 and the negative sign are both constants. They can be pulled out front. So we get something that looks like this. Negative 2 times integral from negative 1 to 1, x, e to the x, dx. So now to finish off this integral, what we need to do is we need to do integration by parts. Because here we have a product of a polynomial function and an exponential function. Those are all those sort of guideline 1 for integration by parts problems. So in this case, my u is going to be my x, dv is going to be e to the x dx, my du is going to be dx, and my v is going to be e to the x. Derivative of x is just 1, dx. Integral of e to the x is e to the x. So I'll have negative 2 times u times v is x e to the x. And that has to go from negative 1 to 1, minus the integral of v, which is e to the x, du, which is just dx, from negative 1 to 1. So now I've just got to integrate and plug in. So this first one, I'll have 1 e to the 1, which is just e to the 1, minus negative 1 e to the negative 1, minus x root of e to the x is just e to the x. That's to go from negative 1 to 1, So this will give you negative 2 e negative 1 is plus e to the negative 1 minus, here is e to the 1 minus e to the negative 1. It'll look like that once I plug in all those limits. And again, I could simplify, but I'm not going to save time. Any questions about example 8 here? Again, this problem required both a substitution as well as an integration by parts. Yes, Katie?
When you change the limits of integration, shouldn't there be a negative sign in front because t is pi and it's negative 1?
Oh, so you'll notice that, thank you. Yes, you're right. This should have been the lower limit, this should have been the upper limit. And then I invisibly changed limits of integration by accident. And I should have, when I did that, I should have put a negative sign in front. So all these future ones, this should have been a positive 2 in the end. Positive 2, positive 2, positive 2. So by the way, usually when you change limits of integration, if it started from the lower limit, it should stay at the lower limit. If it started from the upper limit, it should stay at the upper limit. I accidentally reversed those, which, again, if you reverse limits of integration, it always puts a negative sign in front. And I'm sorry I made that mistake. I think I just, yeah. Okay. Any questions about these guys? Okay. What I'm going to do next is I'm going to talk a little bit about how integration by parts works with applications. The idea is any of the applied problems from Chapter 6 can be used to create integrals that you need to do by parts. Yeah. So, for example, I could ask you to find the average value of this function. And finding the average value requires you to do an integral. If we're integrating this guy, we're going to need to use integration by parts to do it. And on the next test, there is going to be one problem, which is, an application from Chapter 6. So, it's either area or volume or average value or something like that, that requires you to use one of the techniques of integration from Chapter 7. So, again, the only one time you'll have to worry about doing this, but there is going to be something that requires using Chapter 7 stuff to do the integral, as long as using Chapter 6 stuff to set up the integral. So, any of the applications we discussed in Chapter 6 can result in integrals which require the use of integration by parts. Some problems are frequently used in tests and exams because they test more than one topic in a single problem. Again, I like these sorts of problems because they require you to be able to do more than one thing in the same problem. And most real-world problems are like that. There's very few real-world problems that only require integration by parts. They also need you to set up the integrals in the first place. So, here's example 9 here. I want you to use a graph to find an approximate x-coordinate of the points of intersection of these two guys. And then I want to find approximately the area of the region bounded by those two curves. So, let me just pull out a graph. So I want to find the points of intersection of ln x plus 1 and 3x minus x squared. X times there we go, and 3x minus x squared. There we go. So those two functions. If you'll notice, they basically cross at 0, 0 there. So 0, 0 is one point of intersection. The other one here, that point of intersection is between 1.9 and 2, and between 2 and 2.1. And again, you can find those with your graphing calculator. Graphing calculator is this thing that you can find the intersection using the calc menu. So intersection points here are 0, 0, and 1.93, 2.07. I'm just approximating those based upon where this point is located between 1.9 and 2 and between 2 and 2.1. So those are the approximate intersection points. of those two curves. So if I want to find the area between those two curves, I've got to integrate one curve minus the other from one intersection point to the other. So I've got to integrate from here to here, the top curve minus the bottom curve. So I've got to integrate from 1.93 to 2.07, x ln x plus 1 minus 3x minus x squared dx. Now when I do this, the first thing I'm going to mention is that really I can do these two integrals separately because I've got something minus something else.
Yeah.
Oh, wow! And the upper limit should be 1.93. Thank you. I was thinking of this as an interval for some reason. Yeah. 0 to 1.93. They're x coordinates. That's what I was going to be putting in. So here I'm going to have x ln x plus 1 dx. Here, got 3x minus x squared dx. Now, I'm just going to mention that that second integral I can do really easily. The second integral is just a polynomial function. There's no difficulty integrating that. So the second integral will give you 3x squared over 2 minus x cubed over 3 from 0 to 1.93, which will be 3 times 1.93 squared over 2 minus 1.93 cubed over 3. And if we plug in 0 to both of those will give you 0. So you don't have to worry about that lower limit. So basically, this is what the second integral is going to give you. Your calculators could evaluate it. It's the first integral that's going to cause you difficulty. So when we're doing the first integral, that's where we're going to need integration by parts. So here we've got a logarithmic function, so that's going to be my u. And my dv, actually I'm going to actually write it over there, because I'm not going to have space there. So for this first integral, my u is ln x plus 1. My dv is x dx, which means my du is the derivative of ln x plus 1, which is 1 over x plus 1 times the derivative of x plus 1. Derivative of x plus 1 is just 1, so my du is just 1 over x plus 1 dx. My v is x squared over 2. So, okay, so when I do that, that integral will give me u times v, ln x plus 1 times x squared over 2 from 0 to 1.93 minus integral of v, x squared over 2 times du. And now to finish this last integral I'm going to need a substitution for. And the reason for that is because here we've got something on the bottom. So I'm just going to mention that this first part here will give you ln 2.93, because 1.93 plus 1 is 2.93, times 1.93 squared over 2. And if I want to do this last integral, this one that's circled in green, I'm going to do it up over there. That last integral is going to require a substitution. Substitution is going to be u equals x plus 1. So du is dx. And if u is x plus 1, x is u minus 1. Right? Just move the 1 to the other side. Which means this x squared will become a u minus 1 squared. The limits of integration will be from when x is 0, u is 1. When x is 1.93, u is 2.93. X squared will become u minus 1 squared. That's x plus 1 on the 2u on the bottom. Du u minus 1 squared is u squared minus 2u plus 1. There, I can divide each of these things by 2u separately. So u squared over 2u will give me 1/2 of a u. 2u over 2u will give you 1. 1 over 2u will give you 1/2 times 1 over u. And each of those things is something we can integrate. 1/2 u will give you 1/4 u squared. The 1 will give you a u, and the 1/2 times 1 over u will give you 1/2 ln absolute value of u, from 1 to 2.93. And then if we wanted to finish this off, we need to plug in all those things and subtract. I'm not going to, just because I'm realizing my time is a lot shorter than I want it to be. But basically, and this example is going to be significantly more complicated than anything you would ever see on a test. This is like assignment difficulty problem. But pretty much at this point, yes, you could plug in. You've already got this number. You've already got this number. You could plug each of these things in here. 2.93 minus 1, 2.93 minus 1, 2.93 minus plug in 1, and subtract. And you get numbers for each of those intervals. But yeah, there's only half an hour in class, and I want to start the next section at least a little bit. So, any questions about what I've done here so far? Anyways, again, this problem is significantly harder than anything you can see in a test. So, sadly, those aren't a huge good selection of ones that are good difficulty in the book. The ones that are in the book that I have assigned are better difficulty than numbers, like numbers 59 is a better difficulty than number 60 here. I'm also going to skip example 10 here, which is a volume problem. If you want me to do this one, using ln x and calculating the volume of it, which is going to be required integration by parts, right on Muddy's point, parts, and I'll do it on Tuesday's class, like some of that. So, I'm going to move on and start section 7.2. I'm not going to finish section 7.2.1 here. I'm not even going to get halfway through section 7.2. But I told Stan, who's doing Thursday's class, that I would at least start it. So I'm going to do that. And what section 7.2 is on is integrals of sines and cosines. So what we've done with integration by parts, we've done things like if we had an x squared and a sine x. We know how to do that. We've done things where we have an e to the x and a sine x. But if we have a sine x and a cos x, like two different trigonometric functions together, we have not covered those. And that's what section 7.2 is about, is how do you deal with two different trigonometric functions together. And the idea here is based upon how we do an integral like cosine cubed x. So the idea is we might think, because we have cosine of x cubed, we might want to try the substitution u equals cosine x. But the problem is we can't do that because the du in that case would be negative sine x, and there's no negative sine x there to become the du. You can't do substitution unless there's something there that can become at least part of the du. So we cannot use the substitution u equals cosine x. But what we can do is use the substitution u equals sine x. Now this seems counterintuitive at first. Why would we want to do u equals sine x? There's no sine x there. Well, the reason is because we need something to become the du, and what is there that can become the du is one of the cos x's. So if we have this integral cosine cubed x dx, one of the things we can do is write it as cosine squared x times cosine x dx. And if we want to use the substitution u equals sine x, one thing we can do is remember that cosine squared x, is 1 minus sine squared x. And if you look at this, it's a lot easier to do that substitution here. So if u is sine x, du is cos x dx. So this integral will become the integral of 1 minus u squared du. If we take the antiderivative of 1, we get u. Take the antiderivative of u squared, we get u cubed over 3. Plus c. And if we remember that u is sine x, then we get sine x plus, or minus, sorry, sine cubed x over 3 plus c. So the idea here is that the only way to integrate cosine cubed is to split it up as a cosine squared to cosine and to turn that cosine squared into 1 minus sine squared, because that'll allow you to do the substitution u equals sine x. Once we've done that substitution, evaluating the integral is fairly straightforward. So what we're going to be doing when we have sine x's and cos x's together is we're going to try to figure out, is it going to be better to take cosines and turn them into sines, like this, replace cos squared x with 1 minus sine squared x, or is it going to be better to replace 1 minus, or sine squared x with 1 minus cos squared x? Which of those two identities is going to be more useful in that problem? Which of those two identities will allow you to evaluate the integral? And the idea is there are two rules that allow you to do these sorts of problems. And those two rules are going to talk about odd powers of sine and cosine. The idea is the reason this works is because the power of cosine was odd. It was cosine cubed. If we tried to use this strategy with cosine squared, it wouldn't work. So what's going to happen, what makes the odd power special, is that we've got a cosine squared, we've got an even power, and we've got one cosine left over. And that cosine left over is what's going to become the du. So when we're intuiting these sorts of functions, the first thing to look for is what do we have that could be left over to become the du. Once we figure that out, then whatever else is left, whatever even power is left, can be turned into a formula involving the other trigonometric function. So if we have a power of cosine which is odd, our substitution is going to be u equals sine x. In that case, the du will be cosine x. We've got to save one cosine to become the du. And any other cosines, we're going to use the formula cosine squared x is 1 minus sine squared x. So any other cosines will become sines. Similarly, if the power of sine x is odd, we're going to pick u to be cosine x. Therefore, the du will be negative sine x. And any other sines we see will be turned into cosines using this formula. Sine squared x is 1 minus cos squared x. Any questions about these guidelines before I go into some examples? Okay. So I'm going to go through 3 examples here, and then that will be it for today's class. So example 1 wants to do the integral of sine cubed x cosine to the 4th x dx. So this is example 1. Sine cubed x cos 4x dx. So the key thing here is the power of sine is odd. If the power of sine is odd, we want to say, oh, theta is not x's. It doesn't really make a difference, but the power of sine is odd. We want to turn all but one of those sines into cosines. So we're going to write this as sine squared theta times sine theta cosine to the 4th theta d theta. Sine squared will become 1 minus cos squared. And then we're going to sine theta d theta left. Now the substitution we're going to use in this situation, we want the sine theta d theta to be your du. So my u here is going to be cosine theta. Now if u is cosine theta, du is negative sine theta d theta. So this sine theta d theta here will actually become a negative du. And the integral will become 1 minus u squared u to the 4th times negative du. I can pull the negative sign out front. 1 minus u squared times u to the 4th is u to the 4th minus u to the 6th. If I expand that, if we take the antiderivative of u to the 4th, we get u to the 5th over 5. If we take the antiderivative of u to the 6th, we get u to the 7th over 7. And we just need to remember that u is actually cosine theta. So the answer here is cosine to the 5th theta over 5 minus cosine to the 7th theta over 7 plus c.
Did you drop the sign for the bracket?
Oh, thank you. Yes. Thank you, Danielle. Any questions about example 1 here before I do example 2? Okay. What I'm going to mention in example 2 is that this idea can also be combined with other substitutions. It can be combined with integration by parts. So example 2 here, we have the integral of x sine cubed x dx. And the key thing here is we have a product of a polynomial function and a trigonometric function. So using our integration by parts guidelines, we're going to think that u is x and dv is sine cubed x dx. Now, if we want to figure out what v is, we need to figure out how do we integrate sine cubed x. Well, to integrate sine cubed x, we're going to have to split it off as sine squared x times sine x. Sine squared x is 1 minus cos squared x. Now, to integrate this, we're going to need a substitution. T equals cosine x. So dt is negative sine x dx. So this will become integral of 1 minus t squared negative dt. We integrate this. This gives you t minus t cubed over 3. The negative sign comes out front, which is negative cosine x minus cosine cubed x over 3. Right? So sometimes, just to do the integration by parts, we need to do a complicated integral, like sine cubed x. If u is x, du is 1 dx. So finishing off this integral is going to look like this. We're going to have u times v, which is x times negative cos x plus cos cubed x over 3, minus the integral of v, which is negative cos x plus cos cubed x over 3, du. Du is just dx. So it'll become x cos cubed x over 3 minus cos x. Here, we can think about this as the integral of cos x dx plus the integral plus 1/3 times the integral of cos cubed x dx. The integral of cos x is just sine x. That's something that's easy for us to do. The integral of cos cubed x was that example I did at the beginning. It's sine x minus sine cubed x over 3. And then you just have to tack on a plus c on the end. Again, I didn't sort of show all the steps for doing the cos cubed x here because I'd already done that one before. If you do have any of these memorized, like the simple ones like sine cubed or cos cubed, feel free to do this on your test solutions. If you don't have them memorized, you can expand it out the same way I did in the first example, but if you do happen to have them memorized. Now, one thing to mention is if you do have them memorized, I do want to show at least some work for the problem in general. So if I asked you to just do sine cubed, I don't want you to just write out the answer. I want you to show the work for that. But if I ask you for something complicated which involves a sine cubed, and you have this memorized, feel free to sort of write out the answer like that.
Can we memorize like the antiderivative of tan x and stuff like that?
Yeah, yeah. Actually, tan x is one of the ones I'm going to recommend that you do memorize.
Like log and secant.
Yeah. Okay. Sorry, any questions about example 2 before I move on to example 3? Last example I'm going to do for today's class is example 3. Example 3 deals with other trigonometric functions in addition to sines and cosines. This one deals with a cotangent. And the idea is one easy way of dealing with these other trigonometric functions is to write them in terms of sines and cosines. So here we have cotangent to the 5th theta, sine to the 4th theta. So cotangent is the same thing as cosine over sine. Cosine theta to the 5th over sine theta to the 5th is the same thing as cosine to the 5th theta over sine to the 5th theta. All multiplied by sine to the 4th. 4 of the sines are going to be canceled. So I will have here cosine to the 5th theta over sine theta, d theta. So there I've got now just in terms of cosines and sines. Now in this situation, this is going to be another situation where, well, the power of sine is sort of odd, but the power of sine is odd in the denominator. And odd things in the denominator, it's not going to save you a sine theta to be your du. You cannot get a du in the denominator. Substitution does not work that way. So I'm going to need to actually make cos theta into my du. So I'm going to actually have to do u equals sine theta, which means this cosine to the 5th, I will have to write as cosine to the 4th times cosine theta. And the cosine to the 4th, I can write as cosine squared squared. Since cosine squared is 1 minus sine squared, this is 1 minus sine squared squared. That will give you cosine to the 4th. And now I can do my substitution. U is sine theta. Oh, sorry, no, there's no limits of integration. There were no definite integrals. I somehow thought there was a definite integral as one of these, but. So, if u is sine theta, du is cos theta, this becomes the integral of 1 minus u squared squared over u du. If we expand the top there, that gives you 1 minus 2u squared plus u to the 4th all over u. So we have 1 over u minus 2u plus u cubed du. Again, I'm just simplifying it for now so I can integrate it. And if I integrate that, antiderivative of 1 over u is ln of absolute value of u. Antiderivative of 2u is u squared. Antiderivative of u cubed is u to the 4th over 4. So the final answer is going to look like, I'm going to put this in different colors so we can stand out, ln, absolute value of sine theta, minus sine squared theta, that's this thing minus this thing, plus, and we have to continue this on the next line, sine to the fourth theta over 4 plus c. This is the integral of this guy. So again, one thing you will see from a bunch of these problems is some of these integration problems can be fairly long and involved in order to actually get to a final answer. And they can involve multiple different techniques of integration. So yeah, one thing you will see is that there will be, there are not going to be nearly as many integration problems on the next test as there would be like derivative problems on your Calculus 1 tests, just because of how long these problems take to do. And there will, with difficult problems, I will definitely give you hints too. So that's where I'm going to finish off for today. I'm going to give you some group problems before you go. One of the reasons I wanted to get this far was just because I want to make sure I introduce some of these ideas before Stan teaches you some more of them on Thursday's class. I am going to, sorry, where am I looking? Oh yeah, here it is, group problems. So again, you will not have time to finish all 3 of these today. Work on as many as you can. I will go over the solutions to these guys on Tuesday's class when I'm next back. Actually, you know what? No, I will give these ones to Stan to say, can you start with these 3 problems as a review of what we covered last class. So these 2 are integration by parts questions. This one is one of these ones that we just did with an odd power of sine or cosine. So I'm going to give those folks to Stan, say, can you start off with these as extra examples?
Where's that B thing?
It's a beta.
Oh.
It's a Greek letter. If you just think of it as a capital B, it'll give you the same answer. It's just a constant.
Oh.
Yeah. It's just a weird constant because it's a Greek one. I'm also going to hand out some Muddy's point cards. If anyone has anything they want me to go over, again, I will not have a chance to go over any of this until Tuesday's class. Oh, yeah. 476, I think is correct. I think the 5 is a totally typo. Yes. Sorry, no 5,000. Yes, just 476. The page number if you're looking that up. Yeah, if anyone of you have any things you want me to go over on Tuesday's class, put them on my point cards. Again, the next quiz, normally the next quiz will be on Tuesday. It's not going to be on Tuesday. It's going to be Thursday next week because of the fact that Stan's coming in. And I wanted to give you folks a chance to ask me questions before the quiz. So, yeah.